All right, so electron configuration, we just did some examples with. Let's move on. We're actually this, as I said before, shows the shape of the periodic table. You might not recognize it yet, but that's what it does. So the periodic property, the periodic chemical properties. So the electron configurations show what chemical properties different atoms are going to take on. And this is really important, especially in chapter 9 when we get to it. Electrons in the outer orbits are what determine the chemical properties. And the whole thing, the electron configuration, is summarized by the periodic table. So understand that. This thing called the periodic table, here, let's go to it. So here we go. Notice there are rows, okay, which are also known as periods, and there are columns. Okay, so the columns are very important because the elements that are in each column are similar to each other. Okay, so elements in column 1A, notice there's A columns and then there's B columns over here. And then we get back to A columns over here. A column, A column, A column. The A columns are different than the B columns. We'll talk about that in just a little bit. But everything in column 1A has similar chemical properties. Everything in column 1B, they have similar chemical properties. And to some extent that's true for the B columns. For the 3A is pretty much aluminum. 4A. Notice we've crossed over this jagged line. The jagged line distinguishes metals on the left-hand side. So everything on the left-hand side of the jagged line, these are all metals, including aluminum. Right along the jagged line, things like silicon, germanium, and arsenic and tellurium to some extent, and of course boron to a lesser extent, are considered semiconductors. They act like metals in some situations, and then in other situations they act like this group over here to the right hand side of the jagged line. These are called nonmetals. These are all nonmetals. Some stuff like carbon and nitrogen and oxygen, fluorine, right, phosphorus, sulfur, chlorine, right. So these are non-metals, and So notice most of the periodic table, and including these two rows down here, which, by the way, this one is the lanthanide series. So between lanthanide and hafnium, this entire row belongs right here. And this is the actinide series. This row right here goes right here. Notice between 89 and 104. So there's 90 and there's 103. The only reason that they don't put these in and put them down here like this is because it would just make the periodic table look funny. Okay, so get used to that. Get used to the fact that the first two rows are the A's, and then you come over here for 3A is aluminum, and then 4A through 7A, these are all the non-metals. Okay, and they only go down to until you hit this jagged line. Okay, that doesn't, like, for example, notice lead here or tin are not part of group 4A. They don't act like carbon at all. These are clearly metals. And all right, so here, let's go back. And the first column, the 1A column, are called the alkali metals. The second, these are all, this column, 1A, these are all called alkali metals. These 2A, these are all called alkaline earth metals. beryllium, magnesium, calcium, strontium, and barium. This one's radioactive, but this is radium. And then we come to the seventh column. The seventh column: fluorine, chlorine, bromine, iodine. And this one's radioactive. These are all what are called halogens. And then the last column on the periodic table, column 8A, these are called the noble gases: helium, neon, argon, krypton, xenon, and radon. These are special in that, in fact, in the next chapter, we're going to find that all the atoms attempt to look like the noble gases. They attempt to have 8 outer electrons, with the exception of hydrogen, which can only have 2, like helium. So that's a little bit of a preview. But anyhow, these noble gases do not chemically interact with the rest of the periodic table. They're kind of by themselves. They're happy in the configuration that they're in. The 8 outer electrons for these and the 2 outer electrons for helium is a nice stable configuration, and so they stay to themselves. That's why they call them noble gases. Noble being, back in the 19th century, talking about like noble blood, people who were, dukes and barons and things like that, princesses and stuff. They weren't supposed to interact with the commoners. I guess you can imagine, the rest of the periodic table are the commoners. Okay, so the noble blood, the noble gases, as it were, just stay to themselves. Let's see, what else? So the A groups are called the representative groups. That's another name for them. And the B groups are also known, these groups right here, as transition metals. What we're going to find in the next chapter is these don't do the same thing every time, whereas I might as well tell you right now. Column 1, really simple. For them to chemically interact, they tend to lose 1 electron. All the metals, everything over here, tends to lose electrons. The nonmetals tend to gain electrons. Okay, so these, column 1A, they lose 1 electron. Column 2A, they lose 2 electrons. Aluminum, 3A, loses 3 electrons, and that's it. The rest of the metals, you have to, they don't always do the same thing. Sometimes they lose 2, sometimes they lose 1, sometimes they lose 4, it depends. All right, we'll get to that later. These are really simple. So 4A is just pretty much carbon. And so what does carbon do? It will gain, it tries to gain 4 electrons. So it tries to look like neon, right? And so 5A tries to gain 3 electrons. All of the 6A, oxygen and silicon and selenium, try to gain 2 electrons. And the halogens will try to gain 1. Okay, so that's a little bit of a preview to the next chapter, by the way. Here, let me finish this up. So I already talked about this, how you have the representative groups and the non-representative groups. Columns 1, 2, 3 tend to lose electrons. 5 through 7 tend to gain electrons. The semiconductors can act either way. What I want to do now is show you some examples of the dot notation, or sometimes it's called the Lewis dot notation. Oops. Here, let me just go to a. All right. And so notice, by the way, we're going to be using just the representative groups. Okay, so when I do this, and the reason for that is because they always do the same thing. They always have a certain number of electrons around them, and that can be predicted from what column they're in. Let's take let me do a generic example. So there's no element called E, okay, and the way that we do this is to imagine. You don't ever draw this, okay. You imagine a box around the element. So you have a chemical element. You start at right about here. You don't have to start right there, but I always do. And so that would be one electron. That would be like the alkali metals, and then there's another, this is supposed to be a dot, there's another electron, that's the alkaline metals, there's another electron, that's like aluminum, okay, and then now we're at carbon, okay, because it has 4 outer electrons. So notice, and then you just keep going, you repeat around the 4 corners, okay. There's a group 5, because there's 5 outer electrons, a group 6, like oxygen, and then a group 7, like fluorine or chlorine. Okay, so that's the way it works. Let's do chlorine. Okay, so you write the chemical symbol. It's always a capital letter and a lowercase letter if there happens to be a second letter. All right, so chlorine, if we go back to the periodic table, well, I don't have to because I already know it's a halogen, right? So it has 7 outer electrons. So the dot structure would be 1, and I got to be able to see these dots when you turn this stuff in, okay? So do this correctly, show nice good-looking dots. So there's 4 of them, and then there's 5, 6, 7. Okay, so you're always imagining a box, and the reason that we do this, okay, so that's the way it looks right there. That's perfectly fine. That's the Lewis dot structure, or the dot structure for chlorine. Now what I'm going to show you is why this is important. Okay, this is a pair of electrons. This is a pair of electrons. This is a pair of electrons. This is a lone electron, and that lone electron wants to have a partner, basically. Okay, here let's do sulfur, which is very similar to oxygen. Sulfur, if you go back to the periodic table, is in group 6. So it has here. Let's take a quick look at that. Where's my periodic table? It is right there. So there. Let's blow that up a little bit. Here's sulfur. It's in group 6. Do you see that clearly? It's just like oxygen. So oxygen would have the same Lewis dot structure, just to let you know. Alright, so let's get back to my picture here. There we go. And so sulfur has 6, and so here we go, 1, and then the other, the other side of the box is 2, 3, 4, 5, and 6. Okay, these are trying to get them to. All right, so what do we have? This is a pair. This is a pair. Anything along these sides of the imaginary box. Here, let's make that one just a little bit bigger. And so you have a pair, and then there's a single electron, and then a single electron. So sulfur is going to want to have 2 more electrons, one to join this guy, and one to join this guy. Okay, so that's going to be how it interacts chemically. So that's why we do the dot structure. For potassium, it's really simple because it's in group 1. You just put a dot like that. Calcium is group 2, so it's 1 dot and then another dot like that. So that's the dot structure for calcium. There's the dot structure for potassium. All right, good. And that ends the chapter.